Finally, for the sake of completeness, we briefly introduce the multi-layer perception neural networks we have used in this example for the discriminator and the generator. Well, so because we are in this example, we will be dealing with handwritten digits from the very famous dataset NIST. That dataset contains 28 by 28 pixel values for each sample, which is 784 attributes per data sample. So we will accept the size of the image because it's only something like 700 variables. We do not employ the convolutional neural network. We just forcefully collapse everything together into a very long vector, and that's the shape of the data, and we process the data through several layers of multi-layer perception. Lastly, we get a head and produce one score, which is between, because we have employed the sigmoid function to map the value into 0 and 1, so we can interpret that as the probability, and we interpret that probability as the confidence that the discriminator thinks the sample belongs to the true class, which are the true data samples. And seemingly, we create a generator that maps some random distributed variables, the z variables, into the space of 784 dimensional data space. This generator, this model accepts a setting of the latent dimension, which is the distribution, the space of distribution in which the z variable will be sampled, and well, it put the drawed random vector into several layers of neural networks, and finally it maps it into the same shape as the data, and transform the normalization, and then we will have a sample of the data. So here are the two neural network models. Well, for the data, we just use a very standard data loader for using the PyTorch library, as we discussed somewhere in this subject, and I'm sure you can find a lot of tutorials on the internet to introduce the PyTorch and Torch Vision, and especially a lot of tutorials about the NIST dataset. Examples. Here we can see several examples of the generated images using the trained data model. Let me move this here. Yes. So this is the beginning. The G just output some random noise. I think after normalization, nothing left. So after several runs, here is 100 mini batch of training. It starts to, well, just output some random patterns, and this is after 200 mini batch of training. It starts looking like characters, but everything has been mixed together, so you cannot recognize which any meaningful character from that. So if the training is you give the training several times, several hundreds or thousands of iterations, the model starts to improve its modeling of the data distribution of handwritten characters in terms of image pixels. So I think I have trained it for some tens of thousands of mini batches, and look, here is the model's behavior after 30,000 mini batch training, which is pretty quick. And now it's the generated samples starts looking like real characters. Please be noticed that these are just mapped from random sampling of the Z distribution. Those characters, no one had ever written down those characters. This has been learned by the generative model and randomly sampled out. So the model, by the fact that the model is able to generate images like that, in some sense we can say, okay, the model has learned knowledge about what the images of handwritten digits should look like.